Hello everyone, my name is Hästbacka and I'm presenting a work that's been done part of the Productive 4.0 project, and as already mentioned there are quite a number of co-authors in this paper, and the work is a software system architecture basically for utilizing sensor data and implementing various analytics functions in it. First I'm going to give a quick introduction. Then the work is based on two use cases. One is for chain hoists and the other is for vibrating screens. And from these we have derived a number of requirements in order to define this software system architecture, where we strive for flexible and dynamic configuration of information flows as well as the computational services being used. And this is based on the Arrowhead framework that was mentioned in the previous talk by Jari. To start, process and equipment data is needed typically for monitoring and control of the production, but increasingly this is more important also for different value-added services provided, for example, by the device and system manufacturers. And this is especially the case where we have fleet data available, and this can be utilized by the end user. We have a lot of sensors, but increasingly other systems can provide information and act as supplementary sources of data for analytics as well. But the challenge here is that how do we combine and integrate all these information and other system components and services in an interoperable and an efficient way? We want to achieve this kind of a plug-and-play future where we just connect information sources and analytics services, which is the case of this application use case. And this is also in line with what Industry 4.0 and similar initiatives are striving for. We need to be able to dissect our functionality into small modular pieces, for example services in a service-oriented architecture. And then to achieve true interoperability, we cannot only look at the data formats and semantics of data being exchanged, but this goes further to communication protocols and even further to interaction mechanisms like these transaction-like behaviors or message exchange patterns that take place in these complex systems compositions. And we also need to use more efficiently computational resources available locally as well as in the cloud, and be able to optimize and balance where we want to do the things. The problematic part is that how do we maintain security both in closed networks as well as in open internet-based networks. And here we face the fact that we have multiple, let's say, competing interests, competing vendors and operators in the same networks. Then quickly going into the use cases, I will be very brief on these. The first one is for monitoring these quite low-cost chain hoists in shop floors. And the idea is to track events and activities taking place in assembly steps. As these are quite low-cost devices, much calculation cannot actually take place on the hoists themselves, but we need to have something on the gateway level or in the cloud where the analytics is being run. And the second use case is vibrating screens. These are for harsh environments where we crush rocks, and the kind of objective here in this use case is to utilize a number of different kind of heterogeneous sensors as well as information stemming from the control system operating the production line of these screens. For this we identified quite a number of different requirements. I will mention a few of them because we need to pre-process data locally, because in, for example, the vibrating screens example, we cannot transfer everything to the cloud. We need to do it locally, but then there are also several cases where information then want to share it further on, and then we need to be able to run it either on the cloud or do it locally on the edge. Another identified requirement was that we need unified and agreed formats for transmitting information within these application architectures, as well as publishing it further for other consumers, such as those that make more detailed or more further refined analysis of the results. And if we look at all the small sensors and let's say services that are capable of processing data, we need some mechanism to centrally manage where information is flowing and where computation takes place. And this needs to be on the whole application architecture level when we're talking about these systems of systems or systems of cyber-physical systems. Some software and hardware requirements for data interoperability. It's clear that we need some agreed structures, and we based our structures on JSON and XML structures following the Mimosa data model for having the data interoperability of measurements communicated. Then for communication level interoperability, here is where the actual problem is and the challenge in integrating systems of systems. We try to limit the amount of different APIs and have them as uniform as possible. Agree messaging patterns, exchange patterns for decoupled solutions, because it's not always feasible to use these typical request-response communications, but we have decoupled systems that just push information somewhere, for example, to a message bus, and so on. And another point was that to have this interoperability of connecting different systems, we need agreed means to do the discovery, orchestration, and composition of services. And this also includes how to manage authorization and access of different individual, quite stupid or let's say not that complex sensors, for example. For this approach, we defined some requirements for the system components, basically limited to internet communication capable devices or those that can produce information through a gateway. And they need to support either HTTP communication or MQTT for a more decoupled approach. Then for the computational functions, we defined some requirements that they need to be deployed as services to be able to integrate them into this interoperable, flexible architecture. And they should be as agnostic to their physical location and underlying hardware or infrastructure as possible. This means we need to use both ARM-based devices, more limited devices, as well as cloud resources. Quickly to summarize the system architecture that was developed, we have here on the left-hand side, we have devices that provide sensor data. These are primarily used to develop our analytics models, as well as algorithms that are then deployed to the gateway and to various cloud locations. And runtime data is then being fed into these functions or computational services. But how to manage this whole infrastructure at runtime? We have these kind of different services, and we use Arrowhead framework for that. Basically, this means that these services are registered to the service registry, and when the consumer, basically in this case it can be, for example, the device or system producing the sensor measurements, it requests the orchestrator where to store or where to push the data, which services to interact with, whether it should go here or to another one, or maybe both of them. And once the orchestrator finds out which service is available, it gives instructions to this individual instance here how to operate in a bigger composition. It also checks for authorization, provides a token, and then allows the consumer to communicate with the providers. So this device can communicate, for example, with this interface here and same interface here. The challenge, to conclude things, is how do we manage these complex compositions and flexibly changing and dynamically evolving systems. For example, in this analytics use case here, where we might introduce new computational functions to do some calculations or new measurements that we want to utilize in the composition. And for that, we defined a conceptual architecture where we agreed on data models, defined them, and defined a few interchangeable APIs that we configure in the settings, and also message exchange patterns for those systems that communicate using a message bus solution. And the discovery, integration, and interaction mechanisms are here based on the Arrowhead framework, its core services, and using that and the architecture developed here, tailored to that Arrowhead solution, enables us to configure quite flexibly how we route data between these components, where we execute the computation, whether it's locally somewhere or in the cloud, and also to manage security and authorization in a centrally operated fashion, so that individual sensor systems don't need to know who will use it, but still we can manage it securely. Thank you for your attention. Questions?